Okay, hello everybody. It is Monday, start of a new week, March 29th. And what we are going to do today is add one more equation to our quiver of tools when we are trying to do confidence intervals. Now remember, when we're doing confidence intervals, on the one hand, when we're doing confidence intervals, we are usually doing inferential statistics, which means we don't know what reality is. And so we are taking a sample, we're doing an experiment, or we're doing a survey, right, of random selections. And then we will look at the sample we took. We'll look at the random sample we took, because I'm kind of assuming, at least for right now, that everything is random, right? Now, we will look at that sample, and that from that sample, we will get an estimate. We'll get an estimate of the mean, okay, which is usually what we're looking for. Now, once we have that estimate, we are going to say, well, what we got from the sample is the best estimate of what's out there that we have. We know it's not right, but it's the best we have. We know it's not right. As a matter of fact, we're 100% sure it is not exactly right. It came from a sample, right? But what we are going to say is it's the best we have. We are 0% likely that we got it exactly on the nose, right? But what we are trying to do is put a little bit of padding on both sides so we can say something that we're sure of, okay? We want to say something like, we are 90% sure that from our sample, we know that reality is this number plus or minus this amount of padding, right? And, or we want to say we're 95% sure that it's this number plus or minus some padding. The more padding you put around it, the less likely it is you're going to make a mistake, right? So the more padding you put around it, the less likely you're going to make a mistake, but the less valuable your statement is, right? And you can go to the extreme and say, I am 99.999999999% sure the answer is between minus infinity and positive infinity. Okay. Are you 100% sure that the number you're looking for is between minus infinity and positive infinity? Yes. Is it useful? No, that statement is not useful, and your boss will probably fire you, right? So what we're trying to do is put the appropriate amount of padding on both sides so we can make a meaningful statement. We put too much padding on the both sides, your boss is going to look at you and say, that gives me no information whatsoever. But I am 100% sure I'm right. Yeah, but you just gave me something that I can't use, right? If you try to get too narrow, okay, your boss may depend upon it, but there's a higher probability, or sometimes a high probability, that reality is not that close as you thought it was, right? So you've got a very low confidence level that what you're telling your boss is correct because you didn't put enough padding on both sides. All right. So to do this, we have so far used 3 formulas. And today I'm going to introduce a 4th formula for a specific purpose. So let's recap. Let's get a nice chart out here. Erase my economics, and we're going to do statistics. All right. The first formula we had is x bar plus or minus z sigma square root of n. Oops, there we go. X bar plus or minus z sigma square root of n. Right. And when do we use this? We use this formula when sigma is null. Right? Okay. Other things we have here is n is number in sample. X bar is the average of sample. And z is the z value with 50% in between or alpha in between minus z positive z on standard normal. Okay, so depending upon what confidence level we want, okay, if it's 90%, then we will have a z value that has 90% inside of minus 1.645 to positive 1.645. If z is 90, if we're looking for a 95% confidence interval, we will have 5% in both tails, right? And we will have z being minus 1.96 to positive z equals 1.96. And whatever confidence level we want, we figure out what the corresponding z value is, right? So this was formula 1. Okay. Formula 2 was very similar to this. It was x bar plus or minus z s square root of n. Right? Now, this formula here looks almost identical to that one, except instead of sigma, we have S. Why do we use this formula? We use this formula when sigma is not known, right? And n is greater than or equal to 30. If n is greater than or equal to 30, and we don't know what sigma is, we will look at our sample, compute from our sample what our estimate of the sample standard deviation is, S. And if we got this from a sample size that is larger than 30, we say, you know what, good enough for government work, right? And what we do is just say, oh, our n is large, our estimate of sigma by using S is probably pretty good. So let's just replace that sigma. Let's replace that sigma, erase it, and put S in its place, and then go on with life the way we always did. Right? Now, the third one is x bar plus or minus t s square root of n. Notice they all look very similar. But when do we use this third function? We use this third function when sigma isn't known, but n is small. Okay. And what we have is the format looks the same, except we have created enough uncertainty because we don't think our S is as good as it needs to be, okay, that we don't feel comfortable going to the Z table, and we are going to have to adjust for the fact that our S might be wrong. Okay? It adds a little bit more uncertainty to things. Okay? And we don't feel comfortable that we can use the normal table in the back of the book. So what we end up using is the student's T distribution in the back of the book. Okay? And so we look at this formula here to find the appropriate spot. Okay? Now, I am going to find the T table. It's out there on the blackboard. Okay, I've got it there. It is in the back of your book as well, right? Actually, the one I have is a little bit more detailed than the one in the back of the book. But in the back of the book, let's see if I can find the page. It is on page 570. Okay, and I don't know if you guys can read this or not. Okay, but I'm putting it up there so that you can see it is in the back of the book. Okay? And so what we ended up doing is going to the T table and then reading the T table. Now, reading the T table is in one little way confusing, okay? But with the exception of that little tidbit, which is what we call the degrees of freedom, which in our case is going to be n-1, okay? It is actually a very, very easy table to read. As a matter of fact, it is so easy that we're going to use it even when we shouldn't be using it, right? When should we use the T table? When we are doing equation 3. What table should we be using when we are doing either 1 or 2? We should be using the normal table, the Z table. Okay. But a little secret, the last line on almost all T tables is going to give you the Z value. Why? Because as n becomes large, as it becomes very large, the T distribution and the Z distribution in the normal table look like they're pretty much exactly the same thing. Okay. As a matter of fact, if you have an infinite number of observations, you know sigma about as well as you can. Your S is going to be an exceptionally strong estimate of what sigma is. Why? Because you got more than 1 trillion observations, right? Right? So as n becomes large, that T distribution essentially becomes the Z distribution. Okay? Now, and as you are looking at the T table, it is in the columns, the T values are getting closer and closer and closer and closer to what the Z value is, right? As a matter of fact, some tables like the one I think I'm showing you, okay, once you get over n equals 30, it just says, hey, good enough. Don't be bothering with this table anymore. Just go straight down to the Z table. Oh, by the way, I'm going to give you one more column and tell you what the Z value is. Right? Now, the one in your book, okay, will go down to 30, but then it'll also give you a couple other examples of n equals 40. I mean, degrees of freedom equals 40. Degrees of freedom equal 49. Degrees of freedom equals 50, 60. It's got a couple of additional ones, and then it says, oh, okay. Here is the final line, okay, which is the infinite line as far as an infinite number of observations, right? Some books will put an infinite number. Some books will just write this is the z-value, which is essentially the same thing, right? The one in your back of the book uses the infinite symbol. The one that I pulled off the internet that I have out on Blackboard just has the z-value on it. So let me go back and show you how to read the z-value. And then what we're going to do is come up with even go to a fourth version before we get complicated. Yeah, after the fourth version, things get a little bit harder to understand what you're trying to accomplish. Okay, but we'll show it to you anyway. All right, and here goes. So share application screen. What I'm going to go to is the t-table that is on Blackboard. Okay, let me just quickly, before share application, see whether I can find it on my t-table. Yep, I've got it right here. Okay. All right, so let me get you there. Slide application, table. All right. Make this thick. All right. So what you should be seeing is the what is the t-table. Okay. Now, what the t-table is showing you is the shaded area, again, is the probability. But the t-table, as I said last time, works backwards. Where in the z-table, the numbers in the middle of the table corresponded to the shaded area. In this case, the shaded area is shown as one of the top headers for the columns. So this first column here has this being 40%, the shaded area being 40%. Well, if you just imagine another line being on the negative side in the same location, okay, style. If we look at this shaded area right here where my cursor is, okay, if the area to the right where it's shaded is 40%, and this was a shaded 40%, what we would end up with is a t-value that has the negative of this. Notice the t-table, okay, has a bell-shaped curve, just like the normal. It is symmetric. It is centered around 0. So some of the exact same tricks that we played and we learned how to do on the normal table, we can do on the t-table as well. Okay? So in the first column is an illustration of when this shaded area is 40%. If this area, if we were shading the exact same area on the other side, and that was 40%, what would be in the middle? We would have 20% left over in the middle, right? If this were 40%, and that's 40%, that's 80% shaded in the two tails, means there's 20% unshaded. If we were looking at that, which would mean we were looking at what confidence interval? A 20% confidence interval, because we want to say we are 20% sure that we are going to be between this T number and this T number. And if 40% is in this tail and 40% is in that tail, these are the column that would give us 20%. So a 20% confidence interval. Right? If we wanted to do a 90% confidence interval, what would we need to do? Well, if we wanted the shaded area to be 90%, I don't think you guys can read that. Okay, let me make this bigger. Okay. If we want that middle area to be 90%, how much does each tail have to be? The amount on both sides, this tail has to equal what? All right. Let me go and see what you guys just wrote. I can't, since it's showing my screen, I can't see what you guys wrote. I'm assuming somebody wrote 5%, right? Because if that middle is 90%, then what do we have? We have 5% in this tail, right? That would be 5%. And we would have 5% right there. Okay, so if we were looking for a 90% confidence interval, it would be where this shaded area is 5%, which is 0.05, which means we would be in this column right here. Oops. I need to grab that. We would be here in this column. Okay, where in that column? I'm not sure. Right? I can't find it. All right. Well, we would know we're in this column here. Now, which row are we in? Well, notice that the row says degrees of freedom, DF. P stands for, it says degrees of freedom / P for probability, which is this shaded area. The P corresponds to this row. Degrees of freedom is this column. The degrees of freedom is n-1. Why? Because that first observation, when we estimate S, is useless, right? And when you remember that formula, the difference between calculating sigma from a population and calculating S was when we calculated S, there was this magic -1 that showed up in the denominator. Instead of dividing by n, it was divided by n minus 1. If you guys remember that, that was the difference between the formulas for the population standard deviation and the sample standard deviation. The one had that n minus 1 in it. Well, that n minus 1 shows up here again as the degrees of freedom. So if we wanted, okay, I don't know why all of a sudden it lost. There it is. Okay. We know we're in this column. And if our n were 11, 11 minus 1, 11 observations minus 1 is 10, would tell us that we are in the row with the degrees of freedom equals 10. And we would know that our t number we need to be using for a 90% confidence interval using formula 3 is a 1.812. Right? Okay. This particular table goes into a little bit more detail, more decimal places than the one in the book. But anyways, so that's how we do it. Now I had indicated that if you wanted to cheat and use the wrong table for formulas 1 or formulas 2, you can do the same thing here, but go all the way down to the bottom of the table. And if you look at the bottom of the table, there is a Z line, and that Z line here says 1.6448 or 1.645. So this is the T, the Z value that corresponds to 5% in each tail. Remember, 5% in each tail means there's 90% in the interval in the middle. Right? So this is how we use this table. Notice if I wanted to have 6% in this tail and 6% in that tail, okay, that would correspond to an 88% confidence interval. But guess what? There's no column for 6%. So we would have to go look for a much better t-table, okay, if we wanted an 88% confidence interval. But it's 88% is a very weird number for your boss to ever ask you for. Your boss is much more likely to ask for a 90% confidence interval or a 95% confidence interval. Okay. By the way, what's the 95% confidence interval? That's 2.5% in each tail, which means you're in this column. Well, if you wanted to find the Z value in that column, go all the way down. And by the way, 1.959 something or other, or 1.96, right, is that number that you get from this table, right? And that 1.96, I've been drilling into you. You're going to get that all the time, right? So this is how we look at the t-table. Okay. Any questions on using the t-table? Because I'm going to go and talk about one other item. Okay. And this item was, remember we looked at the binomial distribution, right? The next item we are going to deal with is what you basically would do if you were trying to do a binomial distribution backwards. Okay. All right. You guys probably can see me now. Let me see what you guys are seeing. So when I write it on the board here, I can see what I'm writing. So the next formula I am going to give you, and I'm going to look for it on the page. And the page that I am in your book is in chapter 8.1 on page 281, right? And this fourth formula looks very-ish different. Okay. Remember in the binomial distribution, we were looking at things like flipping a coin, and we wanted to flip the coin 6 times and say, okay, what's the probability of getting 1 coin, 2 coins, 3 coins, 4 coins, 5 coins, or all 6 coins turning up heads, right? The binomial distribution had us knowing what the percentage of heads was. And we used a fair coin. Let's see whether Polly is falling asleep, or if I flip my coin, flip it up in the air, flip it up in the air, and it gets stuck in the seat. Okay, normally Polly will run because she loves playing flip the coin. Turned in the heads, but Polly is somewhere else in the apartment, and let's just sleep. All right. If we know a fair coin is 50-50, right? What if I take a coin and I bend it? It's not a fair coin anymore, right? What is the probability when I flip that non-fair coin, that bent coin, that I get a head or a tail? Right? And the bottom line is, I'm not God. I can't do that mathematical modeling. Maybe some of you are physics majors and you would be able to do it, right? But I, as a business person, I can't do it. I don't know this bent coin, how often it's going to be heads, right? But I really want to use this coin, right? As a matter of fact that it's not fair makes me want to use it so much more, because I am an evil person and I like to take that coin and I'm going to start a betting empire based upon my non-fair coins, right? Or using my dice that are loaded with lead in a corner, or starting a baseball team with bats that have cork in them. I'm just a cheater, right? But I'm a cheater and I want to know, well, what is the probability of an event happening, right? I want to know, what is the chance? What is the probability of this unfair coin? Well, God knows what the probability of it being a head is, and we will designate that as high. Awful choice of symbols, right? Your book, just want to verify that your book uses it. Yes, your book uses it as the definition of the true probability. Most other textbooks do not use pi as a symbol, because we all have been ingrained since probably 5th grade that pi is a very special symbol that means one specific thing, which is 3.14 ... right? Well, in your textbook right now, we don't use pi in that context. We use it as being the true probability of success, which is probability of success would be flipping a coin heads, if heads is our definition of success. Right? What is 1 minus pi? 1 minus pi is the probability of when we flip a coin that that coin does not end up with a head, which is the true probability of failure. Okay. Now, the reason your book uses pi and 1 minus pi goes back to that Greek god thing, right? We use Greek letters when we know as much as the Greek gods do, which means we know reality. Okay? But this is where some textbooks, and when I write my textbook, I'm going to differ from this textbook because I will call this P. Okay? And I will call this Q. P and Q. You see this in a lot of textbooks. Okay? So when it gets to creating our equations, okay, P is the real probability of success. Okay? We didn't use the Greek letter this time, or I won't use the Greek letter this time, because the Greek letter of P is pi, and that is just mathematically such a well-known. Pi is 3.14. Okay, I don't think you can use that for anything else, but your stats book does. Okay. 1 minus q, 1 minus pi is the true probability of failure. Okay. Now, as mentioned, most textbooks do not use pi because of that confusion factor. They use P or Q, and half of the ones, well, almost everybody will use P, but they will not use, half of them will not use Q. They will immediately say, well, what is Q? Q, I can't call it Q. What is Q? Q is the same thing as 1 minus E. So some textbooks, like yours, use pi and 1 minus pi. Other textbooks use P and Q, and other textbooks use 1. Okay. So this would be textbook 1, textbook 2, okay, which goes back to what I basically said. Hey, keep your dang textbook when you're done with this class, right? Because when you're trying to pull over this thing together, you may be looking for this pi and the 1 minus pi stuff, right? Okay, and all of a sudden you run into a textbook that has Q's in it, and you say, where the hell did that come from? Right? Well, it's because this particular textbook uses P and Q. This textbook uses P and 1 minus P. They're all exactly the same formulas, but they look different. Right? All right. Now, in each case, P and Q or pi, or 1 minus pi, we don't know what those are. We're trying to estimate them, right? So how do I estimate them? Okay, I will do an experiment. Let me flip the coin 50 times. And what will I get from that 50 times? I will get a sample of 50 observations of heads or tails, right? And after I have flipped it 50 times, I can estimate what I believe pi or p to be, right? Let's say I flip the coin 50 times and I get 40 heads. This is going to be my p bar. The percentage or the probability of getting a head from my sample, my estimate is 40 divided by 50. I flip the coin 40 times, even though I don't know what the odds are of it coming up heads. That's what I'm trying to figure out, right? I don't know it, which is why I'm doing the experiment to start with. I do it 50 times, I get 40 heads, and what do I get? P bar is 0.8, right? Now, what is the probability that I got the P bar is reality? That's what I got out of my 50 flips. It's my reality. It's not God's reality, right? It's my reality, and it's going to be my best guess as to what pi should be, right? What's the probability of me getting that exactly right? 0. Okay. But when I'm doing a proportion like this, okay, the formulas we're going to use are going to look like this. This is going to be our best estimate. Probability we get that best estimate perfect is 0, right? The next thing we're going to do is have to add padding on both sides, just like we did before, right? Now, formula 4, which we use for proportions. Or percentages. Okay. This formula is going to be P bar plus or minus Z, again, at whatever confidence level we are dealing with. And this is where things will look different. Will be the square root of P bar 1 minus P bar, okay, divided by n. Okay. This is in your book, equation 8.3 on page 281. So this is the fourth of the formulas, right? It looks different. It turns out, honestly, it's not different. Okay. The weird thing about the binomial distribution, okay, is that in the binomial distribution, if you know what pi is, or p in the other books, right, if you know that, you happen to also be able to calculate the standard deviation, okay, calculate the standard deviation and the variance, right, of the binomial distribution. And if somebody tells you what pi is, it is a mathematical equation that will tell you what sigma is, right? And if you guys go back and you look at that binomial distribution, what we're really kind of looking at here is when I flip the coin to come up with the proportions, right? If I were to multiply them by that denominator, I would have the binomial distribution. So I take the binomial distribution divided by n to give me the percentage of times that I get ahead, right? Or get a success in this type of field. So anyways, if you guys want to do the math, go back and do the math. Okay? But this is the formula. When you do a proportion formula, there is no need for sigma or s. And this formula does not have a sigma or it does not have an s. What it has is your estimate of what p bar is. And because you know your estimate for p bar, you know 1 minus p bar. Okay? 1 minus p bar is your estimate for q. Again, some other textbooks, that third column, would write it like this: p bar times q bar. What is q bar? 1 minus q bar. Okay? This is the fourth formula. Okay? On Wednesday, we will do the scenario of what we like to think of, what I like to think of, are right Twix, left Twix type problems. When we have two observations, two things, and we want to figure out how much more is one than the other. Okay? How much more chocolate did they put into the left Twix than they put into the right Twix? Or how much more, how better are the reading levels at the end of third grade with teacher Marian Smith versus the reading levels of students coming in to her class in the beginning of the year, school year, right? We want to know that difference. How much added value does she bring to bringing students upwards? You know, there's a whole bunch of these things when we're comparing befores and afters, or we're comparing two to see if they are similar or one has more than the other and stuff like that. So we will do those equations, okay, which is a different business problem on Wednesday. With that, I'm going to call it quits. Remember, on Friday, there is no